Okay, hello everyone. Lesson 6, in the syllabus you have to, A-level syllabus OCR, we have to know as to how people have proved that shells exist. What evidence do they have? Or they put forward for the existence of shells. Let's consider some simply, in some concept in chemistry, if you go through some examples, then the whole thing becomes much simpler to understand. Much simpler to understand. In previous lessons, I was telling you that the idea that electrons are kept in place is because of the nuclear attraction that is holding them in place. Of course, it's logical to think that if the shells are closest to the nucleus, or closer to the nucleus, they are more firmly held, isn't it? So if, for example, again, let's use our good friend sodium as an example. So if the nucleus is there, you've got 2 electrons in there, then you have 8 electrons in the second shell, right? And then you have 1 electron in the third shell. All right then. If you and I embarked on ionization, you better remember what ionization is. Ionization, the very definition of ionization, I say it, you can listen to it a couple of times and maybe write it somewhere, is the energy that you need, the energy required to remove 1 mole of electrons from 1 mole of an element in its gaseous state. Oh, I see. So if I have sodium, but sodium is a metal, yeah? Well, you have to spend some energy to convert that into 1 mole of sodium in gaseous state. You haven't even started ionization yet. You understand? So you have to spend some energy in order to atomize your elements, yeah? It's metal, it's non-metal, we don't care, you have to atomize them. Some of you might be thinking, but some elements are already gases, but then say oxygen is a diatomic gas. You still have to turn it into atomic. You still have to spend energy to turn it into atomic elements in gaseous state. Okay, all right, so I've done that now. So what now? So remember, this amount of energy that you spend, you haven't really started on ionization yet. Then what you have to do, then what is the energy that you have to spend in order to remove 1 mole of electrons from 1 mole of an element in its gaseous state and turn that into sodium 1+ ion in gaseous state? Now, let's take a look at this up and down. In all honesty, which electrons are easiest to remove? Which electron has the least attraction by the nucleus? The electron in the outermost shell, isn't it? This electron over there. So when this electron comes out, we spend the least amount of energy, isn't it? So let's plot something. This guy's got 11 electrons, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then the y-axis is energy in kilojoules per mole, all right? So in order to remove that, let's say I'm not graduating this y-axis. It's the pattern that you want to take a look at. Let's say that you have to spend this amount of energy, a few hundred, and that is gone. Now another thing you have to consider is this: when you have 11, this guy's got 11 protons and 11 electrons around it. When the electron in the outer shell is lost, how many electrons are left now? 10. So now you have 11 protons attracting 10 electrons. So the metallic ions shrink as you get rid of electrons 1 by 1. Or rather, the ionic radius becomes smaller. If sodium was this big, sodium 1+ is this big, which means the remaining electrons are more closely held by the nucleus. Okay, so when we take that out, the next shell is complete, is full, is stable. You know, elements react in order to achieve electron stability. And how do they achieve that? By stabilizing the number of electrons that they need to have. Well, this guy in the second shell has got 8 electrons. You know, it doesn't want to be touched. But then you and I don't give up. We want to go in there and drag more electrons out. Convert sodium 1 plus into sodium 2 plus. Well, I mean, if you want to do that, then we have a job on our hands. And remember, every time that you are taking electrons out, the ratio of protons increases with respect to the number of electrons, right? So the ionic radius becomes smaller and smaller, and it will be harder and harder to take the next electron out. The next 8 of electrons, you have to spend a tremendous amount of more. You know, I mean, if this guy is 400-500 kilojoules, all of a sudden we're talking about thousands of kilojoules. For the second, for the third, for the fourth, for the fifth, for the sixth, for the seventh, for the eighth. 1, 2, 3, 4, 5, 6, 7. 3 and 3, 6, 8. All right. So the next, why have I drawn them in an ascending fashion? Because like I told you, when you take one electron out, it would always be harder to take the next one out, and the next one out, and the next one out. But why are they so close to each other? Because they are all in the same shell. They're all in the same shell. And then imagine you've removed all of that as well. And by now, how many electrons have you lost? 9 electrons. So it's these two that are really, really now close to the nucleus. And again, for the same reason, you want to get rid of these guys, the 1s2 electrons. Again, like I said, you've got a job on your hand. There's going to be a massive jump again, those two over there. So if we want to connect these lines somehow, let's do this slowly so it will respond to my... So what is happening? What are we seeing here? What we are seeing here is that there are 3 distinctive clusters of electrons, yeah? And then there are 2 jumps between them. 3 different types of electrons or clusters of electrons means this guy's got 3 shells, right? And the first electron and electrons that you lose will tell you how many electrons are in the outer shell. Therefore, you can identify where is this element, which group this element is from. And when you have 3 shells, it means it must be in the 3rd period. It is in the 3rd period, and it's got 1 electron in the outer shell. So it's our good friend sodium, isn't it? And if you had 2 electrons here to get rid of, magnesium, etc. Remember, the least amount of energy is spent getting rid of the electrons in the outermost shell, right? So this is how they prove that these shells actually exist and how many electrons there are in them, etc., etc. Now, the other things that they could ask you is, or you could be asked is, write the equation for the 4th ionization of sodium. You say 4th ionization, well, okay, if it is the 4th ionization, it means sodium already has gone through 3 ionization already. And then it's losing another 1 mole of electrons to turn into sodium 4 plus in gaseous state. Right? You can write the electron on the left side, or you can take it on the other side and write plus electron. You know, it doesn't matter. It's exactly the same thing. So the ionization for the 4th ionization of sodium is that it already must have gone through 3 ionizations already. And don't forget the gaseous state. You write this equation without that G for gas, you just lost yourself a mark. Totally unnecessarily. Okay, I think we keep this nice and sweet and short, and then that's it. That's it for this one as well. All right. Okay, great stuff.